So, okay, today's lecture is the 13th lecture, and we will study the channel capacity, and then we will see some of the examples. So I think 3 examples I have today. So one example will be a general discussion, and then later we have 2 specific problems based on the general example. So first slide here. So when you consider the memory-less discrete channel with the input alphabet x prime. So x prime is the input alphabet, and based on its transmission, you are expecting some outcome, that is y prime. So that's basically the transition probability. That means you transmit xj, and then you will be expecting what is yk. What is the symbol here? In case of binary channel, either you may transmit 0 and you get maybe 0 or 1 as yk, or you transmit 1, that is xj is equal to 1, you get yk either 0 or 1. Then the mutual information, we have seen this equation, is represented this way: I of x prime comma y prime, that is nothing but probability. There's a joint probability between xj and yk. That means these two occurring together. Log of conditional probability here, that is you transmit xj, but what's the probability of occurrence of yk? Maybe 0 or 1, divided by the probability of the output yk. So this is computed for all the input symbols and also all the output possible symbols. Okay, here the joint probability is represented this way. We know this. That is nothing but joint probability is nothing but the input probability of input multiplied by the probability of output with respect to the input. And also the probability of output is what? Is nothing but probability of input multiplied by the conditional probability of output for all possible input symbols. So with these, it is essential to know also the input probability to find the mutual information. So if we know the input probabilities, then we can try to maximize this parameter, that's the mutual information. Now, the channel capacity, now we will be arriving at the equation of channel capacity. So the channel capacity of a discrete memoryless channel is maximum average mutual information. It's represented as the maximum mutual information in any single channel, that is just a single interval, when where the maximization is over all possible input probability distributions. So what's the meaning of that? Capacity here is equal to maximum of mutual informations, where this mutual information is computed for every instance of the input probability distribution pxj. So how to represent this? Because if you have some probability for input, for example, if you consider a binary scenario, this xj value is what? Either 0 or 1. Right? So if it is 0, for example, if xj is 0, so 0, or it can be 1. In another instance, it can be 1. Right? So if it is 0, then you find out what's the value of this, the mutual information. That is, you will be knowing what's the probability of xj being 0. What's the probability here? Maybe some value, right, between 0 to 1, a value, maybe 0.5 or 0.6 and so on. Then you find out what's the mutual information I, x prime, y prime. And then you get a value here for mutual information I, right, for the corresponding value of xj or probability of xj, where xj is equal to 0. Probability of xj Okay, you get some value for I. Maybe what's the mutual information? I just write a value here, 5. I don't know. I just write an example. Okay, then again, another value of xj. What's the possible value of xj? Possible value of xj is 1. So then what's the probability of xj equal to 1? There is some value, right? So probability. We should know that. What's the probability? That should be the input. Probability of xj. Now xj is equal to 1. What's the probability? Maybe 0.4 or 0.5, 0.6, any value. Then using that, you find out the mutual information I, right? You're finding this value again. Then what do you get? You get some value, right? Result of this computation. Maybe that value is 4. 4. In this case, you need to, what's the channel capacity? Channel capacity is maximum of 5 and 4. What's the maximum value? That is 5, right? Maximum of this 5. So channel capacity is 5. That is the meaning of this paragraph here, or that's the meaning of this equation here. So basically, capacity is nothing but the maximum value of the mutual information for various settings of probability of input. So in the binary case, the input can be 0 or 1. So accordingly, we will be knowing their probabilities. Probability of xj is equal to 0, or probability of xj is equal to 1. Maybe these values, maybe some fractional value is 0.4 or 0.6. Probabilities, I'm talking about probabilities. Probability here may be 0.6. Okay, then using that value, you find out the mutual information. We have seen how to find the mutual information in the previous slide, and that should result in some value. For example, the value may be 5 in the first case, value may be 4 in the second case. Then you'll be choosing maximum between those two, maximum. Okay. Maximum of 4 and 5 is 5. So that is the channel capacity C. So this is the meaning of this equation. Okay. Then now P is a function only of the transition probabilities. That is P probability of output provided the probability of input, or the value of input. And in a binary symmetric channel, we have seen what's the meaning of binary symmetric channel. We know that the probability of inputs are equal. That is, your input may be 0 or your input may be 1. What's the probability? They have an equal probability. That's equal to half, right? The probability of input being 0 is half. The probability that input is 1 is also half. Then channel capacity is nothing but just the information, mutual information between x and y, between these symbols. Okay, the standard relation, that is conditional probability of y0 when the input is 1 is equal to the conditional probability y is equal to y1 provided x is 0, that is p. And then the other case, when x is 0, what's the probability of y0? That's equal to x is 1 and output is 1. The other case is 1 minus p. That means if this 2 occurs with the probability of p for x0 and x1, the other case for x0 and x1, the output being y0 and y1, that is the same, right? You transmit x1, you get y1, or at the input you transmit 0, you get output also 0. The same case, what you transmit, you get that. Its probability is 1 minus p. And another case, you transmit 0 and you get output as 1. or you transmit 1 and you get an output as a 0, its probability is p. These are the two cases, right? If one is p, other one is 1 minus p. So when you add up this, the total probability becomes p plus 1 minus p, that is 1, the total probability, right? Okay, so now if we analyze this further for a binary case, because we are talking about binary symmetric channel. In case of binary symmetric channel, we have two symbols, 0 or 1. So input can have two values, that is j. Output then will have two values, right? 0 or 1. So 2 is because of that, because it's a binary symmetric channel. Then if we use this idea into the information, mutual information, the same equation here, what we have saw in the first slide, then what will be the channel capacity? Because channel capacity is nothing but the mutual information itself. This is a mutual information. That itself is a channel capacity. But for this is a generalized equation. But in this case, we are considering a binary symmetric channel where we consider the j value is varying from 1 to 2. I mean, there are only two candidates here. J is equal to 0 and j is equal to 1. Two summations. Similarly, k has only two summations. K is equal to 0 and k is equal to 1. And also I said that inputs occur with the equal probability. So probability of x0 is equal to probability of x1, that's equal to half. So that when you compute the entropy, what will be the entropy? So entropy is nothing but total probabilities, right? I mean, entropy of this input is nothing but, how to write entropy if you know the probability? Minus p log p, right? Okay, so that is minus p log p plus the second term, 1 minus p log 1 minus p, right? I'm just connecting between the probability and entropy. Okay, so using that, we can come to this equation. C is equal to 1 plus p log p, the other term, 1 minus p log 1 minus p. So this 1 comes from, so you know this is because of this case, and this is because of this case. And 1 comes because the probabilities are equal. So when you have equal probability, probability of x0 is equal to probability of x1 is equal to half, both are equal to half, then total probability is 1. So x prime, its probability is nothing but probability of log p log 1 by p plus 1 minus p log 1 by 1 minus p. So then c becomes, c is equal to 1 minus x cap or x prime, its probability. So this becomes a final equation for the channel capacity in case of a BSC, binary symmetric channel. Okay, so this is the final equation. And now, so this is the end of this discussion regarding the channel capacity, how to find the channel capacity. Now we will see some general cases, and then we will solve two examples. So this example, right now, what I'm going to discuss is a generalized example. Please watch it carefully because we will be using the same idea in the whichever problem you are going to solve today. So first one is regarding the channel matrix. I introduced this term here, channel matrix. What is a channel matrix? So we will try to understand that here. So when you know what are the inputs you want to supply to a channel and you get some outputs, right? So this relationship between input and output as a conditional probability, we represent it as a matrix, that is a channel matrix. So here, memoryless discrete channels are completely specified by the set of conditional probabilities that relate the probability of each input symbol to the probability of the input symbol, output and input. Okay, so each output symbol to the probability of the input symbol. So this is just a definition or brief idea, but here I can explain you in more detail. For example, there are two symbols here, x1 and x2. These are the two inputs we want to send through this channel. This is a channel, and this is the place where you collect the outputs. So if you transmit x1, you get y1, or you transmit x1, you get y1 here. This should be y2. Please make a change here as y2. Okay. Then if you transmit x2, then you get y1 here, or if you transmit x2, when it comes through the channel, it may become y2. Okay, then we write this relationship between the input and the output this way: transition probability or conditional probability. Because when you transmit x1 and it moves through the channel to the output, transiting through the channel to the output, then this is the probability that you get this particular output y1. So it is written here. You will be sending a specific input x1. You know what you're going to send. Then you will be waiting with interest at output. What will be the value of this particular output y1? So that is the conditional probability of y1. You know what is the input, and then you will be expecting or waiting what will be the output here. That is this output point, that is y1. So that probability, maybe it is 0.5 or 0.6, any value. So that is the conditional probability or transition probability. Similarly, when you transmit x1 and you wait here for the output, you know what you have transmitted, that is x1, and now you are eagerly waiting for y2. What would be y2? Whether it is 0 or 1, you don't know. You are just suspecting what would be y2. So that is a conditional probability of y2, provided you know what is your input x1. Similarly, in this case, you know what you have transmitted, x2. You have transmitted x2 maybe 0 or 1. And now you do not know what is y1. You are expecting with a certain probability, maybe 50% there is a chance that y1 will be 1 or it is 0. Similarly, this case, you have transmitted x2. You know what's the value of x2. x2 is 0. Now you are waiting at the output, this point, y2 point. What would be the output, y2? What's the probability of that? Is it 0.4? Is it just 40% that I would get a 1 here, where the input was also 1? Or I get a 0 here, where the input was also 0, and so on. So this is a transition or condition probability. So this relationship we can represent in the form of a matrix that is called the channel matrix. So basically, channel matrix, as defined in this sentence, maybe this is a little complicated, that says what's the relationship between input and output as a conditional probability or as a transition probability. So we can represent the channel matrix for this particular setting this way. So that is nothing but you know what are the inputs and you want to know what is the output, what's the probability of getting these outputs. So x and y are the random variables. These variables holds the value of x1, x2, that is ex will be holding the values of either x1 or x2 or both, and y is caps y, that will be holding the values of y1 and y2. So that's represented here. So you can consider something like this, maybe to understand it easily. So this here you have x, x1, x2. Okay, here you have y, y1, y2, right? So now you see here what we have written. Probability of y1 provided you transmit x1. This is x1, right? So in this row, if you see everything is x1, you transmit some x1, one of the input, and then check what is the probability of getting y1. You transmitted x1, then you check what is the probability of getting y2. That's what is written here along the row. So along the row, your input will remain the same. For one particular input, you will be seeing what's the probability of getting the output at one of the points here, or for the same input, what's the probability of getting the output at some other point y2, that is here. And in the next row, you will be shifting to the second possible input. So x2 is the input. Now if your input is x2, then what's the probability of getting output y1? Similarly, if your input is x2, what's the probability of getting output y2? So this is the channel matrix. And yes, so now you can observe one property here, or one special feature here. When you sum up this, that is probability of y1 x1 plus probability of y2 x2, that is row wise, what you should get? Can you think? Maybe you keep thinking. I will get the answers from you later. Okay, now if we have three cases, then how this should look like? That is three outputs. So probability of output, you know that what you're going to transmit. So x1, x2 are the two inputs you're going to transmit. At the output points, there are three, y1, y2, and y3. So in this, so this is not binary, right? Because you have three outputs, you have two inputs. So this case says the channel matrix is possible for any case. It need not be just a square matrix. Input and output should be same. No, that is not the case. You can have more outputs also. In this case, you have only two inputs, but there are three output points, y1, y2, y3. Then how to write the channel matrix? The same way. For a common input, you are just predicting what will be the output for y1, y2, or y3. The other case, you transmit the second input, x2, and check what will be the probability of getting y1, or what is the probability of getting y2, and what's the probability of getting y3, and so on. Similarly, if you have more inputs also, you can keep writing things as a channel matrix. So this is just an example of a case where you have a channel matrix representation possible even if it's not a square matrix, or you have different number of inputs as well as different number of outputs. Okay, so the answer to the previous question, I asked you to keep thinking. That is, when you consider the probabilities along the row, that will sum up to 1, right? Because you will be transmitting the same item or same alphabet or symbol, x1. And then x1 can come at the output as y3, or x1 may appear at the output as y2, or x1 may appear at the output as y1. If you sum up this, it should be equal to 1, right? Maybe this is 20% chance, this is a 30% chance, then this should be 50% chance. So altogether it becomes 100%. Or in case of probabilities, it sums up to 1. So this is the meaning here. When you sum up all the j's here, outputs, for a specific value of input, your input is common and you are seeing what will be the different probabilities of outputs, then that summation will be equal to 1. Okay, now we have a numerical example for the same case. Probability of the output when you know some input. The channel matrix is represented here. So x1, x2, y1, y2, y3. So when you sum up these three, you're getting 1, right? Similarly here, when you transmit x2, there is 0.2 probability that it will become y1. When you transmit x2, there is 0.8 probability that the output becomes y2. When you transmit x2, there is 0 chance probability that it becomes y3. It will never happen. Either it should be this or this. So anyway, you sum up these three, that becomes 1. 0.2, 0.8, 0. The sum is 1. Similarly here, 0.8 and these two, it becomes 1, right? Yeah, that's what's shown here. Okay, channel matrix, when it is useful, or what is the significance of writing the channel matrix? Channel matrix is useful in finding the probabilities of the output symbols given the probabilities of the input symbols. That's what I said. You know the input probabilities x, maybe x1 or x2, and then you want to find out what's the probability of getting a particular y, maybe y1, y2, or y3, in general, yj. Okay, now the probabilities of the input symbols. How to write the probability of input symbol? Please remember all these equations or terms. Probability of input, because x is a random variable that can represent the symbol x1 or x2. So its probability is nothing but probability of x1 and probability of x2. It's a matrix. If you have more inputs, they will come here along the row. It's a row matrix, right? And then the probability of the output symbol. What's the probability of the output symbol? Probability of y, right? Because y is a random variable that holds the value of y1, y2, or y3. So its probabilities are represented as p of y1, p of y2, and p of y3. So altogether, the probability of the output symbol y is nothing but probability of x multiplied by the conditional probability of y with respect to x, because when you send some input x, it propagates through the channel. Channel will introduce some transition, right? Channel may send it as it is, or channel may send it in a different way. We don't know. That's why we have a condition probability here. Based on some input, you are uncertain about what's the output. That's why P of y is nothing but the probability of input multiplied by the condition probability. So that becomes a total output probability. Whereas input, you see, it is just the input probability is what you send with, because input is totally, you have the freedom of choosing maybe with what percentage you want to transmit. But once you transmit it, it propagates through the channel, then it is not in your control, right? Channel may modify the symbol in any way it wants. I mean, it may happen in any way. So our output is slightly unpredictable or uncertain. That's why for the output representation, you have this condition probability as a multiplying term. Okay, now here, probability of y, as we have seen, is nothing but probability of input multiplied by conditional probability of output. So that's what we are representing here. Probability of x. How to write probability of x? Maybe probability of x1, probability of x2. That's what is written here. Basically, this is the equation. We are substituting the appropriate terms here. So probability of y is equal to probability of x. What's probability of x? That is this, right? Multiplied by this term, probability of, the channel matrix. That is probability of y1, probability of y2, probability of y3 for a specific input. As for the second input, what's the probability of getting these three outputs? Conditional probabilities. Okay, next. The term is joint probability matrix. So here we will have a general discussion regarding joint, that is JPM, and then we will solve the example. So here, probability, that's a joint probability of xy. That is, x and y maybe x1 y1, x2 y2, or x1 y2, x2 y1, they occurring together. What's the probability that we see here? So joint probability matrix JPM is represented like this. So P joint probability x comma y is nothing but probability of x1 y1, probability of x1 y2. Okay, that is x1 and x1 for a common input. Your various outputs y1, y2, when they occur together as a pair, that means you send x1 and you get y1. What is that probability? And you send x1, but you get y2, something different. Then what's the probability? These are different values, right? Maybe 0.2, 0.4, or some values, that probabilities. What is that probability? That is what you are writing here. Next case is probability of x2. You are sending the second input and you are getting an output y1, and you are sending the second input and you're getting an output y2. So basically, again, if you see this row corresponds to x1 and this row corresponds to x2, and this column corresponds to y1 and this column corresponds to y2. So you will be just writing the different combinations that you can form by the intersection of a row and column that you are writing here. Okay, this can also be written as probability. There's a joint probability between x and y is nothing but you have a new term here, PDX. I will tell you what is that, multiplied by the conditional probability of y and x. Okay, we have seen what is conditional probability of yx. It's a channel matrix itself, right? And then you have to see what is PDX. That is a diagonal matrix. PDX is nothing but a diagonal matrix. In this diagonal matrix, you know what's a diagonal matrix in mathematics, right? Having probabilities of the input along the diagonal. So in a case of a diagonal matrix, you have the diagonal elements and other elements should be 0, right? So here, probability along this diagonal, you have the probability of various input symbols. For example, for x1, what's the probability? For x2, what is the probability? So this is the diagonal matrix. So that is represented as PD of x. So when you multiply that with the conditional probability, you should be getting the joint probability. This is the theory. Okay, you can verify that in our examples. We will verify that. So yeah, this is the relation that we have seen. How to write that? I mean, the joint probability, how to write it? x1 y1, x1 y2, x2 y1, x2 y2. That is this term I'm writing here. That's equal to the diagonal matrix multiplied by the channel matrix, right? Or the conditional probability of getting y1 or getting y2 for a specific input x1, and probability of getting y1 or y2 for a specific input x2, right? So basically this equation is substituted with the appropriate terms here. Okay, further simplification is nothing but multiplication between this matrix and this matrix. So you know how to multiply the matrices. So you have this row, you multiply by this column and you get this element here. Similarly, you multiply this row and the second column and you get the values here. Altogether, you represent it as, I mean, next you multiply this and right here, and then you multiply this item. And basically, what I'm talking is about the matrix multiplication. Okay, now, so that is how you find out JPM, joint probability matrix, given the input probabilities. And then we will see some of the properties of JPM. So the sum of probabilities of the ith row of JPM gives the input probability. Is it so? ith row, this row, right? That should give us the input probabilities. That is probability, joint probability of between xi and yj. You're finding the summation for all the outputs, because we are talking about the ith row. Here a row is common, but the column varies because j is varying here, right? J is equal to 1 to n. J represents what? Output, yj. So you are changing the outputs for a common value of the input. That means same row. When you sum up those probabilities here, then that's equal to the probability of the input symbol xi, right? Okay. Next, the sum of the probabilities of the jth column of JPM gives the output probabilities. I have highlighted some or underlined some keywords here. Jth column, when you sum up those probabilities, you get the output probabilities. If you consider the ith row and sum up those probabilities, here you get the input probability. So, okay, that we have seen. We will see the next condition here. The jth column, when you sum up, that is here, joint probability of xi, yj, and we find the summation of these probabilities for what? I varying from 1 to m. What is I? I represents input. It's the index to the input term x. So xi. So basically you are maintaining yj constant, and you will be varying xi, right, for different values of I. Then what happens when you sum up that? That means you are moving from moving along the same column between different rows, because this is constant, one column. When you sum up that, you get the probability of the output j. Okay, the third one, sum of all elements of a JPM is equal to 1. So this is very straightforward from the discussion. When you sum up row as well as column, your joint probability should be equal to 1. Okay, so this is the theoretical discussion. Right now, we'll move on to some examples here based on the today's discussion. So the first example here, I have 2 examples. Let us try to finish that. Otherwise, we will also finish one, and the next one you can take it as a homework. Okay, the first one we will see. Consider the binary input-output channel shown. So this is the channel that is shown. Here it's a binary channel. You have the 2 inputs x1 and x2, and accordingly you get some outputs y1 and y2. And what's the probability? When you transmit x1, you get y1. The probability is 0.7. When you transmit x1, you get y2. The probability is 0.3. Similarly, for x2, you see the values. Okay. And what is the probability of these inputs? They occur with the equal probability. x1 will occur with the probability of 0.5. I'm talking about this x1. And x2 will also occur with the same probability of 0.5. I'm talking about this x2. In this setting, first one, define the channel matrix of the channel. I mean, this is the channel given. You find out the channel matrix. So this we have seen in today's discussion, how to find out the channel matrix given the channel. I mean, all these probabilities, transition probabilities. In the second case, find the probability of output y1. What's the probabilities of output y1? This we have seen an exclusive equation to find out the probability of y1, right? Because output y1 depends on the probability of input and also the transition probability from input to output. And then we also find the joint probability, say probability of x1, y1, and there's a joint probability and a joint probability between x2 and y1. So all these 3 cases we have seen in the previous slides, right? So you should be in a position to solve it by yourself. So if you have a paper and pen, try to solve this. And okay, I will anyway solve this. First case is channel matrix. So how to find the channel matrix? Channel matrix is nothing but the conditional probability of y and x, right? Probability of y provided you know the input probabilities. So channel probability is nothing but you have x1, x2 here, and two outputs y1 and y2 here. So x1, y1, what's the probability? That is 0.7. x1, y2, what's the probability? That is 0.3. Is it so? We will just check, go back and check. x1, y1, what's the probability? That is 0.7. And x1, y2, what's the probability? That is 0.3. Similarly, x2, y1, what's the probability? That is 0.4. And x2, y2, it is 0.6, right? So 0.4 and 0.6 are mentioned. This is the channel matrix. And then we know some details, that is probability of y. We need to find out next the probability of y, that's output. So probability of output is what? That is the product of the probability of input and the conditional probability. So what is px? Px is nothing but whatever input symbols you have, their probability of x1 and probability of x2. Do we know these values? Of course, yes, because this is straightforward from the given question. We know probability of x1 and x2 as 0.25 each. So that leads us to get these values. That is, probability of x1 is 0.5 and probability of x2 is also 0.5. Then, since we know these values right now, that is to find out the probability of output, py, we need to know the probability of the input. We know that. And we also should know this term, probability of output, or sorry, the conditional probability or the channel matrix that is here. So right now it's basic math where you will be multiplying two matrices. Yes, something like this. Probability of output, that is what we want to find out. That's the second part of the question. P of y is what? Probability of the first symbol or the probability of the second symbol. That is what? That's equal to this term or this term, which is this term, or this is the values are 0.5 and 0.5 multiplied by this term, or that value is here. So you just perform the matrix multiplication, this row, this column, you get the first item in the resultant matrix. This and this you multiply. Okay, so you should be getting the values of y1 and y2 after this multiplication. Okay, so everything is clear? My voice is audible?
Yes, sir.
Yes, thank you. Okay, now we have probability of y1, y2 is nothing but 0.55 and 0.45. That is from the multiplication in the previous slide. So this value becomes the probability of y1, and probability of y2 will be this value. So if you sum up these two, should be getting 1. So this is the second question, very straightforward. And the third question is joint probability between x and y. How to find out? We have seen this equation. That is nothing but the diagonal matrix probability multiplied by the conditional probability between y and x. And here we have the diagonal matrix represented this way, where we have probability of x1 and probability of x2 along the diagonal, and rest of the elements becomes 0. This you need to multiply with the conditional probability or the channel matrix. We already have the data to do these substitutions here in this equation. So we will just move ahead and do that. So here, joint probability is here. That is between x and y. Probability of x1, y1, probability of x1 and y2. And here, probability of x to y1 and probability of x to y2. That is nothing but this whole term or this matrix comes from here. Joint probability of x and y. X and y are the random variables. They hold the value x1, x2, that is x. And y1, y2 are the symbols that are represented by this random variable y here. Okay, that's equal to these two terms. So this is a diagonal matrix. The probability of x1 is 0.5. Similarly, probability of second input is also 0.5. And we multiply by the conditional probability or the channel matrix here. So this multiplication again is a straightforward, simple math. And finally, you should be getting some 4 elements, right? Yes. So when you multiply this row and this column, you get the first item as 0.35. This row and this column, you get the second item. This row and this row, you get the third item. And this row and this column, you just multiply and get the final item here. So this represents the joint probabilities between x1, y1, x2, y2, x1, y2, and x2, y2. So these are the total probabilities if we sum up. Should be getting nearly 1. And this is how we find the joint probability matrix. I mean, this is the joint probability matrix, and these are the different elements. So how to represent JPM? JPM is a matrix where the first value is 0.35, second value is 0.15, third value is 0.2, and fourth value is 0.3. So these 4 values, you write it as a matrix, then that's your final answer, JPM. So this is how you find out the different parameters that we discussed. So this question is was asked in maybe a few years before. In several times, it was asked in the test final exams. Okay, now I have some ready reference for you because we talked about conditional probability, joint probability, Bayes equation, all those. So Bayes equation is a fundamental for all this, but you have a ready reference here. You can just refer these equations. These are the ready equations. Whenever you want to find out, maybe. Okay, so this is not actually conditional probability and joint probability because we are talking about the entropies here. Okay, so you know the joint probability or conditional probability, then how to find out the conditional entropy or joint entropy? That is what given here. So this list, I mean, you can have a mapping between joint probability, conditional probability, and the entropies from this table. Okay, you can refer it to this later on, and you can make a note of this. This will help you in solving their problems because these are the ready equations. So whenever you see this term, then if you know this term as well as this term, you can just substitute and find out this. Or you know these terms, just the input, then you can find out h of x. Okay, I mean, you can use it wisely wherever necessary. Okay, now I'll move on to the second example. Again, second example is something similar to the discussions we did in the previous slides, but there may be some differences. So we will revisit that again. So in this case, we are provided with a channel matrix. We have a channel matrix here. The question is, draw the channel diagram. It's a reverse, right? Compared to the previous example where the channel was given, we need to write the channel matrix. But now the channel matrix is given. We need to find out how will be the channel. I mean, we need to draw the channel diagram. The second case, we are provided with the probability of the inputs x1, x2. They have an equal probability 0.5. Then find the probabilities of the output symbols. Outputs are y1, y2. You need to find out that. And then find the joint probability between x1, y1, x2, y1. Selectively, they have chosen 2 items here. In the previous example, we found all of them, but here it's sufficient if you represent only 2. Okay, so this can be taken as a homework, but I will quickly go through the key points. It looks similar to the previous example. Okay, so here we have the channel matrix. Now let us find out how to draw the channel. What's the meaning here? X1, Y1. So we have X2, Y1. So that means you have two inputs, right? The two inputs here. And there are three outputs, Y1, Y2, Y3. You need to connect between X1, Y1, X1, Y2, X2, Y3, and so on, based on this table. So X1, Y1 is 0.8. And X1, Y2, it is 0.2. Similarly, X1 and Y3, nothing. So X1 and Y3, there is nothing. So now arrow is being pointed from X1 to Y3. And similarly, X2 does not go to Y1. So you do not have a edge from X2 to Y1. Otherwise, you have the edges in the rest of the places with a probability of 0.2 and 0.8. That's how you map between the matrix and the channel. Or if the channel is given, you find out the matrix. It's very straightforward. Okay, then you need to find out the output probabilities, because we know what are the input probabilities, that is 0.5 and 0.5, and output probability is computed with this help of this equation. So the condition probability of the channel matrix we know already. Just find the product of these two and you should be getting the output. Okay, here. And now the next point is joint probability. So between X and Y, there is nothing but the diagonal matrix and the channel matrix multiplication. And diagonal matrix is here, and the element values should be 0.5 here as well as 0.5 here. They are the inputs. And we already know how is the structure, or what are the elements of this particular matrix, joint probability matrix. And we're just going for a multiplication here, matrix multiplication, which is this matrix is a 2 cross 2 matrix, and this is a 2 cross 3. So you should get this output. And here now, X1, Y1, where is X1, Y1? 0.4. And X2, Y1 is here. What is this item? X1, Y2. What is this? X1, Y3. Right? So in the question they asked, the question was to find out this value as well as this value. Since you have all the values here in this matrix, you need to just pick the required values, because this is X1, Y1. And this is what? X2, Y1, X2, Y2, X2, Y3. So whichever you need, just pick it up and write here. So this is the end of today's lecture.